Alright guys, for your second video, we're going to focus on slides 52 through the end, and these slides are going to focus on enthalpies of formation, so change in enthalpy or standard enthalpy of formation. And we are going to describe enthalpy of formation as the enthalpy change in which a compound is made from its constituent elements. So I have in the reactants all of these elements, and they're coming together and they're reacting to form a compound. So we call that just enthalpy of formation. I am taking elements and I am forming a product, or I'm forming a compound, and I want to know how much energy am I going to need, or how much energy will we be releasing when we're forming these particular compounds. So that's what this is really looking at. Enthalpy of formation, we are going to symbolize that as delta H, so I still have that change in enthalpy, but it's also going to have this subscript with the lowercase f, and that's going to represent formation. So this is my enthalpy of formation. We can also call this heat of formation, so you will hear those things interchangeably. So if I say enthalpy of formation, or if I call it heat of formation, those mean the exact same thing. And we're going to symbolize that with delta HF. And again, that's just saying that I have elements and I'm going to make a compound, and I just want to know, or I'm forming a compound, and we just want to find that overall change in enthalpy when we're taking those elements, reacting them, and forming one compound. So enthalpy of formation, we're forming a compound. Now, we also have something called standard enthalpy of formation. And standard enthalpy of formation, we are going to denote with the symbol delta HF, so that's my enthalpy of formation. But when it's standard enthalpy of formation, we add that little degree sign up in the superscript. Now, what standard enthalpy of formation is, we have, in the lab, found experimental values for delta H when we have certain compounds. We know certain compounds can absorb a specific amount of energy or possibly release a specific amount of energy when they're formed. So in the back of your book, it's Appendix C, which is page 1059. So if you were to look in the back of your book, Appendix C, you have a column here for thermochemical quantities. It'll tell you the substance, and then it will tell you your standard enthalpy of formation values. So I can find these values there. So this is just a chart that says maybe a couple of them, but page 1059 in the back of your book will tell you all of those if you need any to look those up, and we'll be using that as a reference. You will also probably need this as a reference, page 1059 or throughout Appendix C for some of your homework problems. So standard enthalpy of formation. The standard comes from that we have measured these values under standard conditions. So our standard conditions are 25 degrees Celsius or 298 Kelvin, and then 1 atmosphere pressure. So when you see the degree sign up in that superscript, or if we're talking about standard enthalpy of formation, that means that experimentally we have found these values under standard conditions, which are 25 degrees Celsius and 1 atmosphere. Okay, when we look at reactions, specifically when we're looking at an enthalpy of formation reaction, there are some key things that I want us to add to our notes that we're going to need to follow. Okay, so if elements are in their standard state, and if we produce or form 1 mole of a compound in its standard state, then I can say that my change in enthalpy is my enthalpy of formation, because I'm taking elements, I'm reacting them to form one product, and if they're in their standard states, then I can call that a standard enthalpy of formation. And we're going to look at a couple reactions here in just a second to determine if they're considered standard enthalpy of formation reactions or not. So to do that, we're going to need a couple little key pieces of information that may help us. If our reactants are in their elemental form, if I have reactants that are elements, then that would be a good indication that that would be a standard enthalpy of formation reaction. Number 2, if the elements or the reactants and the products are in their standard state, that will tell me that I have a standard state or a standard enthalpy of formation reaction. And number 3, I need to make sure that we only have 1 mole of product that's formed in our standard enthalpy of formation reactions. So I want to use these 3 key pieces to determine if reactions are considered a standard enthalpy of formation reaction. So I want to go back to our PowerPoint slide, to the next one. This question asks, for which of these reactions at 25 degrees Celsius and let's say 1 atmosphere of pressure, does the enthalpy change represent a standard enthalpy of formation? So I have 3 reactions here, and I want to determine if these represent a standard enthalpy of formation. Am I taking elements? Am I reacting elements to form one product? Are they all in their standard states? And am I making 1 mole of product? For the reactions that we say do not represent a standard enthalpy of formation, what changes should we make so then that way we can get an enthalpy of formation reaction? So let's look at the first one. I have solid sodium, so I have solid Na, and let's think about that. Sodium is an alkali metal. We know then that metals are solids, so it makes sense that an alkali metal, sodium, would be a solid. I have sodium reacting with oxygen gas. I have sodium and oxygen, those are elements. And if I look at my product side, I'm making Na2O. Now if I'm making sodium oxide, then I need to see that it's coming from its elements on the reactant side. I made 1 product over here. They came together to form a compound. I have 1 mole of it, so that follows one of my rules. I see that these are in their standard states. I'm starting with a metal that's solid. I have oxygen that would be gas. And I made 1 mole, again, of the product. Elements, my compound is over here on the product side. This reaction will follow a standard enthalpy of formation. So this first one is an example of a standard enthalpy of formation reaction. Let's look at the second one. On the second reaction, I have 2K, so I have potassium, but that's in liquid form. So I have 2 potassium, liquid form, plus chlorine gas is going to make potassium chloride. Does this follow my rules, my reactions, or my key little steps that we just looked at? So first thing, do I have elements that are my reactants? I have potassium, I have chlorine. Okay, those are in their elemental form, so that one applies. Are they in their standard states? Well, I made salt here. I made potassium chloride, so that's a solid. Chlorine gas, I know that chlorine is a gas here. But potassium is an alkali metal, so its standard state would not be a liquid form. So this right now will not follow a standard enthalpy of formation. But there's another reason why it won't follow standard enthalpy of formation, and that's because we said we only want to produce 1 mole of product. But how many moles of product do I have here? I have 2. So there's actually 2 reasons why this reaction is not considered to be a standard enthalpy of formation reaction. I made 2 moles of product, and potassium is not in its standard state because it's in a liquid form, but we know potassium is an alkali metal, so it would make more sense in its standard state that it would be a solid. So let's change this then, because they asked me, what changes do I need to make then to that equation? So I was given this. I know that potassium should be a solid since it's a metal. And then I have chlorine gas, we said that was fine, and then that would make potassium chloride. Okay, well I also have the problem that, so we fixed the first problem, but the second problem was that we made 2 moles of our product, but I only want 1 mole of product. So if I want this to be 1 mole of KCl, I have 1 mole here of potassium, so those are balanced, but I have 2 chlorine. So what coefficient will I have to write to only get that 1 chlorine here on the reactant side? We'd have to do a half. So remember, we're only using those halves, or the 3 halves or the 5 halves. We're only doing that half of one because we're talking about these thermochemical equations or these thermochemical reactions. That is the only time we can do these halves. Otherwise, we need those simple whole number ratios. So now we fix this reaction, and this reaction would represent a standard enthalpy of formation reaction for this one. Okay, let's look at the next one, or our last one. I have C6H12O6, and it's decomposing into carbon, which is in the diamond form, and then I have hydrogen gas that's also formed, and then oxygen gas. So we said that standard enthalpy of formation would be where we're taking elements, reacting them to form a product, a compound. But this is actually the opposite of what's happening here. I have a compound that's decomposing into these. So I can see here that if this is the opposite, I would say I'd have to flip that reaction. So for this to be in standard enthalpy of formation, I'd have to flip it. So I would have my carbon plus my hydrogen gas plus my oxygen gas would be making then, I have 1 mole of product here, so that's good, that follows that rule. So I have 1 mole of product. So if I flipped this reaction, then I could have my standard enthalpy of formation reaction. Okay, if you have questions on this, make sure you post on the blog so that way we can go over these together, okay? So, or we can maybe go over some more together. On Monday, I'm going to give you some practice with like everything kind of from the chapter so that way we can have a pretty good review. In terms of calculations of the standard enthalpy of formation, if I wanted to calculate delta HF, the standard version of that, I could possibly do Hess's law, but, and we've done that before, we have our 3 steps. In this case, this is the reaction that I'm wanting, and let's say that it happens in 3 steps. I have my C3H8 decomposing into graphite or carbon in terms of graphite and hydrogen gas. But then I have the graphite reacting with maybe oxygen in the air to form CO2, and then I have that hydrogen gas reacting with oxygen to form water. So this reaction took place because of these 3 steps here. And we could have done Hess's law and found delta H. So if I gave you those delta H values over here on the side. But there's kind of a faster way that we can do this as well. We know that these 3 equations, when we sum them up, would make our overall reaction that we want. And again, we could have used Hess's law. If I gave you those delta H values over here on the side, we could have manipulated these 3, done what we needed to, and added that up to get our delta H value. But we could also use our Appendix C, our standard enthalpy of formation values, our delta HF values. Guys, please make sure that you add a degree sign here because this should be delta H formation, standard enthalpy of formation. So please make sure you add that degree sign up here. Please, please, please. Okay, we could use Hess's law in a different way. And it's actually not really doing Hess's law at all. It's actually doing something totally different. So we could use the values of our standard enthalpy of formations that we have in Appendix C by doing delta H is equal to the sum of the standard enthalpy of formations of the products minus the standard enthalpy of formations of the reactants. This N here is just going to represent that stoichiometric coefficient. M here just represents that stoichiometric coefficient. Okay, what on earth do I mean here? So this is my reaction. C3H8 gas plus 5 oxygens that are in the gaseous form will produce 3 moles of carbon dioxide gas and 4 moles of water, of liquid water. So let me just rewrite that out on the Promethean board, okay? Let's just go through this process slowly. I have C3H8 gas plus 5O2 gas produces 3 CO2 gas plus 4 H2O liquid. So if I look in Appendix C, I'm going to look up C3H8, I'm going to look up O2, I'm going to look up the standard enthalpy of formation for CO2 and the standard enthalpy of formation of H2O. And I know if I wanted to find the overall delta H, that would be equal to the standard enthalpy of formations of the products minus the standard enthalpy of formations of the reactants. So products are over here, my reactants are over here. So let's look up the value of CO2 in Appendix C. And if I did that, I would find that CO2 has a standard enthalpy of formation value of a negative 393.5 kilojoules. So CO2, if I look in the back of my book, would have a delta H F value of 393.5 kilojoules. If I look up water, I would find that water has a delta H value of negative 285.8 kilojoules. If I looked up C3H8, I would find that that has a value of negative 103.85 kilojoules. And if I look up oxygen, I find that oxygen is 0. Why would oxygen be 0? Oxygen is 0 because it's not forming from anything else. It's in its elemental form. I just find oxygen already. So since it's not forming from something else, it doesn't have a standard enthalpy of formation because it's not forming from something else. I just find O2 naturally. So that's why our value then for O2 is just 0 kilojoules. So I looked up all of the delta HF, or standard change in enthalpy of formations for all of my products and my reactants. Now I just want to plug this stuff in and do my products minus my reactants to find my overall delta H value. So, products, CO2, H2O. I know that CO2 has a heat of formation value that is negative 393.5 kilojoules. But how many moles of CO2 do I have? I have 3. So I need to make sure that I multiply that delta H value by 3. Okay, so my products, I have one more product. So I have, this is my products plus my water, because that was a product. And that water has a delta H value of negative 285.8, but I have 4 of them. So I want to do 4 times negative 285.8 kilojoules. So here are my products. And I'm subtracting that, so minus my reactants, which I'm going to write down here below. My reactants, I have 1 mole of C3H8. So I'm just going to do 1 times, so I'm going to write the 1, guys, just so we remember that this was just 1 mole. So I have 1 times that negative 103.85 kilojoules, and then plus oxygen. I have 5 moles of oxygen, but my delta H there is 0, so it's just 5 times 0, which you know is just 0. So if I do this math, I do my 3 times this one plus 4 times the negative 285.8, get a number here. I do my math here, and I'm subtracting these 2 numbers. I should get my delta H value to be equal to a negative 2219.9 kilojoules. And that is totally not good with significant figures. We should have 4. So it should be 2220 with the decimal place there. So let's go back. 2220 decimal place kilojoules, because that would give us 4 significant figures there. So all I have to do is look up my reactants and my products in Appendix C to find their delta H or their standard enthalpy of formation values. Once I do that, I can do products minus reactants, make sure I multiply by coefficients, and then I'll get my delta H value. It is really just that simple. So let's go back to our slide. I did all of that work here for you. So that's the same thing that we did here, and then I just simplified it down so we got our answer here. Did we say that? I don't know, guys, if we made, yeah, we did make that negative. I just wanted to make sure that we were consistent. Okay, so guidelines to kind of help remember. Decomposition is the reverse formation reaction. So when we're thinking about, and this is just, I think, remembering overall in general for anything. Decomposition reactions, reverse formation reaction, so I would just use the opposite version of that. So if my delta H value for a decomposition reaction was positive, then if I reverse it, it would be negative. Stoichiometric coefficients, make sure that you remember in your reaction, if there is 3 carbon dioxides, I need to multiply that delta H value by 3. If there's 4 moles of water, I need to make sure that I multiply my standard enthalpy of formation value by 4. So just make sure that you remember those stoichiometric coefficients. Okay, so let's do an example here. So I have calculate the standard enthalpy change for the combustion of 1 mole of benzene, which is C6H6, that's liquid, to carbon dioxide gas and water. So carbon dioxide gas and water. Okay, let's go to our Promethean board. So I have C6H6, which was a liquid, is reacting with oxygen gas to produce CO2 gas and water. Okay, and for this equation, they will actually give you this reaction. So I'm just going to give you this already balanced. So 15 halves, that should be 6 CO2 and 3 H2O. Okay. So based on this reaction here, I want to calculate the standard enthalpy change for this. So I want to find that delta H, and to do that, I can look up my standard enthalpy of formation values in Appendix C, and I know that my delta H would be those standard enthalpy of formation values for the products minus the ones for the reactants. Guys, I would like you to try this one on your own by using the Appendix C. So use the values in Appendix C, and if you do that, you should get your delta H value to be a negative 3,267 kilojoules. So if you look up your values, you should be able to find those on your own. And you should be able to do this calculation on your own, because it's, remember, just products minus reactants. Okay, in part B, they asked us to compare the quantity of heat produced by the combustion of 1 gram of propane with that produced by 1 gram of benzene. So propane has the formula C3H8. And benzene has the formula C6H6, which they would give you on the AP test. So they would say propane, which is C3H8. They would say benzene, which is C6H6. So I know I could look in my Appendix C and find that the amount of heat that's produced when I combust propane, if I look in Appendix C, I would get negative 2220 kilojoules. If I look at the same thing for C6H6, I find a negative 3267 kilojoules. And that would be per mole, if I had 1 mole of them. Okay, but now I want to compare if I had kilojoules per gram. How much heat would be produced per gram? Right now I just know kilojoules per mole, but I want to know or compare kilojoules per gram. So if I wanted to get rid of the mole, I could use molar mass for each of them. So I know for C3H8, that mass would be 44.1 grams, and C